introduce the speaker of this section, and the first speaker is Marjeta Kramar Fijavz. Sorry if it is not pronounced correctly. And she will speak about operator semigroups on vector lattices. Please.
Thank you, Federica. So first of all, I'm very glad to attend the conference in Russia. This is my first time in Russia. Unfortunately, online, but maybe next time it will be also live. And then I also need to apologize to the... I noticed actually that I'm in a session where many talks are on metric graphs or equations on metric graphs. It's been already previously, and also the talk after me will be on this topic. And although I did work a lot on this topic in the last 15 years, I decided to talk about something else on this conference. So I apologize. Everybody who would like to hear about metric graphs should leave now. I have chosen a little bit different topic, which is also not entirely new to some of the people in the audience, because this is the topic I've been working together with my PhD student Michael Kaplin and a colleague Marko Kandic for the last couple of years. So Michael successfully defended his thesis in autumn, but I hope me and Marko and maybe somebody else as well will join us and develop this theory, which I find interesting, fascinating. Okay, so luckily this conference is called One Parameter Semigroups of Operators, and this is exactly what I will talk about. So it will be one parameter semigroups of operators, but these semigroups will not be strongly continuous. So this is something which the majority of the audience is not used to. And another thing that I will change, so it is a almost ongoing dispute which spaces are more important, Hilbert spaces or Banach spaces. So I choose not to take any of them. So I will not even consider Banach spaces. And I will go to vector lattices to be even more general. And okay, let's first start. Just to recall, maybe some of you already have forgotten what is a vector lattice, because it's too simple, this object. Everybody thinks about Banach spaces or even Banach lattices. Vector lattice is just a real vector space with some order relation, such that this relation is also, it forms also a lattice, so we can have a supremum of any two elements or infimum, and the operations are behave well with the addition and multiplication by positive scalars. It is also these objects are also called Riesz spaces. Maybe some of you are more familiar with this name, Riesz space. So it is an ordered vector space which is also a lattice somehow. And of course, if we have additionally to this, if you also have a norm such that this norm is compatible with the lattice, so with the absolute value, which is maybe I should have to first define. Let me first define the following notions. So we can take with x plus, we will take all denote the classical positive cone of all the elements that are bigger than 0 in this order. And then we can have the positive part, the negative part, and the absolute value of any element in a vector lattice. And if this x additionally has a norm that is compatible with this absolute value, meaning that if if two elements absolute value of x is smaller than absolute value of y, then the norm of x is smaller than the norm of y. And if this space is also complete in this norm, then this is a Banach lattice, which we all know. But I will most of the talk I will not talk about Banach lattices. I will just take the vector lattice. So we have a space, vector space, and we do not have any norm here a priori on this space. Of course, I will also have some norms on typical examples, but a priori we don't have any space. We just have this structure. But nevertheless, we would like to define some convergence on this space, some continuity relations. So I need something else to define this, and we have chosen the so-called relatively uniformly convergence, which is defined here. So a net in my space X converges relatively uniformly if there exists an element U, such as for each epsilon there exists an index alpha naught, so that X alpha, the absolute value of X alpha minus X is smaller or equal than epsilon times U for all indices alpha bigger than alpha naught. And this U that appears here is called a regulator of this net. And if I say that a net converges relatively uniformly, then it also means that I can find such a U that this holds. And this is my theorem of convergence that I will use throughout the talk today. Just to give you some examples so that you can understand what this notion means. So if we are, for example, on function spaces, functions, so these are continuous functions with compact support, omega is some locally compact Hausdorff space, and then a net of functions will converge relatively uniformly on this space if and only if it converges in the supremum norm, which exists in this space. But this is not enough, so this is not equivalent to this convergence. Additionally, there must exist a compact set K and an index such that my net is 0 outside this compact set for indices big enough. So this is relative uniform convergence in this context, for example. So of course there are also other terms of convergence also on vector spaces. Actually there are many, and we have chosen this one because we found it the most suitable. You will see it has nice properties, but for example the most maybe well-known convergence is so-called order convergence, right? And in fact, this RU convergence implies order convergence. So, but they are not the same. They are only the same on the LP spaces. So if we have a net of functions on LP spaces, then they converge RU if and only if they converge in order, for example. But for general spaces, it is only this direction. From RU convergence, order convergence follow, but we have counterexamples. It does not follow vice versa. Okay, so this is now this is the basis. We have vector lattice and we have this convergence. Now we need continuity. And so continuity is actually defined the same. So we have a function. I will just talk about positive functions because this will be used for the semigroups later on. The function is called RU continuous, or I will also abbreviate it with RUC, which means relatively uniformly continuous. If we can find a regulator function U, such that for each epsilon there exists a delta, such that this absolute value of f in h plus t minus f in t is less or equal epsilon times U for all t and all h small enough. So smaller than delta plus this. And this is now my continuity that I will use, and I will just denote, I will just write this with this arrow with RU on top of it, or RU limit I will call RU limit in this sense. And similarly, I did not put all the definitions here, but you can imagine that now I can use this also to define RU derivative. I just take the RU limit of the differential quotient. I can define RU integral, just taking the Riemann integral, the Riemann sums, and limiting this RU notion. One can show all usual properties one has for the integrals. So one can develop the RU calculus just as the usual calculus. So we have all these theorems, Newton-Leibniz theorems, fundamental theorems, everything. So this is now our tool we will use to define semigroups on it. And now, what is now my object of interest? I have a family of linear operators on a vector lattice. And this family is called a relatively uniformly continuous, or RUC semigroup for short, if it is a semigroup. So one parameter semigroup, as we are all used to it. And if it is continuous in this RU sense. So for every x, the mapping T mapping to TTX in X is RU continuous. So that this T in H plus TX converges in RU to TTX as H converges to 0. So this is my definition. And also throughout this talk, I will assume that the semigroup is positive, meaning that every operator TT is positive operator on X. One could reduce this, but everything is much simpler if I assume positive operators. Okay. Now, some properties of such objects. The first property turns out to be actually the most important one. We know that for the usual strongly continuous semigroups, we have that the orbits are bounded on bounded intervals. And something similar holds here as well. So if you have a positive RUC semigroup on a vector lattice, then the set of the absolute value of TTX for T on a bounded interval is order bounded. And this is actually, I think, the most important property. It was the first lemma that we proved, and actually we use this in almost every proof afterwards, because it is one of the most important ingredients that we have. If you compare to the strongly continuous semigroup theory, of course, here we do not have norms, so many things do not carry over, but this is one of the few things that do. So this is something that really helps us. And the first things where this lemma plays a role is in showing this result, that actually RU continuity, it suffices to show RU continuity only for positive elements on the positive cone and only at 0. And then it is translated. This is the same as the C0 semigroups, but and this is that eases our proofs for RU continuity. Okay, maybe another remark, which is of course important, is that if we also have a Banach lattice, then the positive RUC semigroup is automatically also strongly continuous. So this is a generalization of this term. It is not, it does not hold backwards. So if you have a positive strongly continuous semigroup on a Banach lattice, it is not automatically RU continuous. But it is if and only if this first property holds. Okay. So if this holds, then the strongly continuous semigroup would be RUC continuous on a Banach lattice. So it is a generalization of the strong continuity on Banach lattice, it seems that this is a proper thing to consider. Examples, of course, you want examples. The first classical example, the left translation semigroup, the easiest one in semigroup theory, but on which space? So it turns out that this is relatively uniformly continuous semigroup on a bunch of spaces that are not Banach. For example, a space of Lipschitz functions on a whole real axis, uniformly continuous functions with compact support, or even continuous function on a whole real axis, where translation is even not strongly continuous, for example. But it is RU continuous on here. And however, it is not this always relatively uniformly continuous. So it is not relatively continuous on LP spaces, for example, which is not that nice. And however, one can find a vector sublattice of an LP space where this left translation semigroup will be strongly continuous, will be RU continuous with the Sobolev space, W1P. Here again, we obtain relative uniform continuity, for example. And these are all vector lattices, although not all also Banach spaces, right? So far our theories, you see, we have some generalizations from the Banach space theory, or even we can even consider some non-convex spaces. For example, we can also consider P between 0 and 1 with some other examples. One non-trivial example, Orsztyn-Uhlenbeck semigroup, which is here given just in this Mailer formula for gamma is some Gaussian measure. I just state this here. Of course, not so easy to prove that this is really a relatively uniformly continuous semigroup on this space, but we were able to do so. So we have also some non-trivial examples. Okay, now I hope I have convinced you that these objects exist. Now, the next question is, of course, the generation of the semigroups. And here you see that actually we were able to carry over many results from the strongly continuous semigroup case. The first one, okay, first we need to define the generator. We just define it as usual, just the limit is taken in the RU sense. So the limit of the differential quotient. And it is, the domain is whenever this limit exists. Example for our left translation group, for example, on the CC of R, the generator is the classical first derivative, and the domain are the functions that are continuously differentiable. So, okay. Now our question is, of course, okay, if you have a semigroup, you can define the generator like this. But now, of course, the most interesting question is if one can go vice versa. So if you have a generator, first of all, what are the properties of an operator to be a generator, and which semigroup does it generate, or is there a unique semigroup such that this operator is a generator? So I can answer positively to first part. Okay, first I need to define some new terms, which are actually all clearly go the same way as the classicals. I just take RU in front. So a set in X is called RU dense if for each X there exists a sequence that RU converges to this X. And then the operator would be RU densely defined if its domain is RU dense, and it is RU closed when it is closed in accordance to this RU convergence. So this is just the same. And actually it is very easy to show that every generator of a positive RUC semigroup is RU closed and RU densely defined, and the proof goes almost literally as the proof for the strongly continuous case, where the same holds, of course. However, it is not immediately clear whether the generator determines the semigroup uniquely. So this is the question that it is not so easy to solve here in the RU continuous case. We will leave this will be our last result, actually. Okay. Another thing that does not carry over is exponential boundedness. This is also something that we all know, that for the strong continuous case, every strongly continuous semigroup is exponentially bounded. But here, this is not the case, so I need to define this specially. I call it exponentially order bounded because I take the absolute value of TTX. I also need an X here because I don't have a norm. And so a semigroup is exponential order bounded of type omega if for each X there exists U, again this regulator U on the right-hand side, such that for all T, the absolute value of TTX is more or equal e to omega T to U. And for example, our left translation semigroup, one can show that it is exponentially order bounded on spaces of Lipschitz functions, uniformly continuous functions, or this Sobolev space, but it is not exponentially order bounded of the spaces of continuous functions, for example. So this is also something that does not hold always. We cannot take it for granted. And it turns out that if we want to study generation results, we need to assume this. And so this will be our assumptions later on. Okay, here I also define the resolvent for the positive resolvent set. And then one can show actually that if we have an exponentially order bounded positive Rhesus semigroup, then the resolvent of its generator can be obtained by this Laplace integral, so by this integral formula of the semigroup. So we can obtain this result only if we have an exponentially order bounded semigroup. This is something we need to assume. Okay, and now I would like to state the most important result, the generation result that tells us when is an operator a generator. So we were able to prove the Hilo-Yoshida type result, but we also needed another assumption which seems very complicated, and we are still not sure whether it is essential or not. But let me try to explain this to you. So there are many tools here that we cannot use. For example, in semigroup theory, we really like, we'll use a lot uniform boundedness principle or these classical theorems, which we do not have at hand here. That's why we need all these other technical details. And this is actually something that will replace this uniform boundedness principle in this case. So we call a vector lattice X has property D. If for each net of linear operators, the following two assertions would imply that it converges to 0 in the RU meaning. And what are the assertions? First one is that we have the RU convergence on a dense subset. And the second one is a little bit more complicated. It combines sequences of elements and nets of operators. So if you have a sequence with that RU converges to 0, there exists a regulator and appropriate indices such that alpha xn absolute value RU goes to 0, so it's more than epsilon times U for indices big enough. So this seems like a very strange property, but we were able to find many other properties that actually all imply this property. This is why it's called D, because we also have property C and so on. But D also stands for the density. So this is why we need it actually. And actually, all vector lattices we tried, all I named you today, they all have this property. As a matter of fact, we were not able to find any vector lattices which does not have this property. So this is an open question. So maybe this is even always fulfilled. I don't know. So this is actually open. So if you are able to find an example of a vector lattice without D, this property D, I would be interested, of course. Or prove that all the vector lattices has it. But for now, we don't know this, so we have to assume this. And why we need this is this lemma is the answer why we need this, because if a vector lattice has a property D, and our group is exponentially order bounded positive, then it is enough to show RU convergence on a dense set to see that the semigroup is relatively uniformly continuous on the whole set. And this is something which is usually done in the semigroup theory, because you take the domain of the operator which is dense, and you operate, you perform everything on the domain, and then you just extend it. And now that we have this at hand, we can formulate the main generation theorem, Hille-Yoshida type theorem. So we have our RU complete vector lattice with property D. Then the following is equivalent. A is a generator of an exponentially order bounded positive RUC semigroup. If and only if it is RU closed, RU densely defined, and for each lambda one have these resolvent estimates which resemble the resolvent estimates we have by the Hille-Yoshida theorem. Okay. I wanted to say a little bit of the proof, but I think I will skip this. It is actually the classical, you follow the classical lines, just one need to perform many more calculations, but the idea is the same as Yoshida idea of the approximation. But my last proposition is now, having this generation result, one can also prove that the generator determines the positive exponential order bounded RUC semigroup uniquely. But this follows from the Hille-Yoshida theorem. So the semigroup which is constructed there is unique. This object is unique. Okay, this is short. Of course, there are many things to do. I have named here a few. This is an open, we have now doors open. We are now working on approximation, perturbation theory. We are looking for interesting applications. Of course, there are other convergences we would like to study and compare with the one I showed you today, etc., etc. But time is up, so thank you. If you have some questions, I'm welcome.
Thank you, Marjeta, for this interesting talk. So we have just some short time for some short questions.
Can I ask a question? You have mentioned two types of such semigroups. One is a shift semigroup, and the second is a semigroup connected with Ornstein-Uhlenbeck process. My question is, it is possible to characterize all semigroups, say, on the space continuous function on R, so one-dimensional case, which are connected with differential equations. I mean, first order or second order. It is possible to characterize them because you have only two examples.
No, I have also other examples, of course. Also, the heat equation is also an example on appropriate space, or I mean, there are other examples as well. So I cannot characterize it now. And the translation semigroup is actually just one example from all these. One can, I don't know if you are familiar with these Kopman semigroups.
Yeah, it's very easy to check if you have translation semigroup, but of course, Ornstein-Uhlenbeck semigroup is more difficult. So maybe I was thinking that it will be possible to characterize some parabolic equations which have such semigroups, which generate such semigroup. It will be interesting subject.
Yeah, it would be interesting to consider. Yes, I agree. But we have not done this yet. No, we were just we were happy to find as many examples as possible at the first stage. So this was the, Thank you.